Quantum mechanics, the branch of physics that delves into the behavior of the smallest particles in the universe, has long captivated our imagination with its mind-bending concepts and counterintuitive phenomena. Among its enigmatic principles is the notion of wave tracing, a fundamental concept that provides a unique perspective into the nature of quantum particles and their interactions. At the heart of quantum wave tracing lies the concept of a wave function. In the quantum world, particles such as electrons, protons, and photons are described not as classical objects with well-defined properties, but rather as probability distributions represented by wave functions. These wave functions encode information about a particle's possible position, momentum, and other observable attributes. Imagine a tiny electron buzzing around in space. Its behavior is not predetermined, but rather governed by probabilities. This probabilistic nature is where wave tracing comes into play. When we talk about tracing the quantum wave, we're essentially following the evolution of the wave function over time to understand how it changes and how it influences the behavior of the particle it represents. To dive into the process of quantum wave tracing, let's consider a simple scenario, the famous double-slit experiment. In this experiment, a beam of particles, such as electrons, is directed at a barrier with two closely spaced slits. As the particles pass through the slits and strike a screen on the other side, an interference pattern emerges, much like ripples in a pond created by two overlapping waves. This pattern suggests that particles, despite their seemingly solid nature, exhibit wave-like properties. Wave tracing plays a crucial role in understanding the double-slit experiment. Initially, the particle's wave function is a superposition, a combination of all possible paths it could take. As the particle travels through the slits, its wave function spreads out and interferes with itself, creating the characteristic pattern on the screen. The act of tracing the wave involves calculating the probabilities at different points on the screen, revealing the likelihood of the particle's presence at each location. Now, let's take a quantum leap and explore how wave tracing becomes even more intriguing with entanglement. Entanglement is a phenomenon where two or more particles become deeply interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. Imagine two entangled electrons. When the state of one electron changes, the state of the other changes instantaneously. In the realm of wave tracing, entanglement leads to a fascinating dance. When entangled particles are separated and their wave functions traced, the act of observing one particle instantaneously determines the state of the other, regardless of the distance between them. This phenomenon challenges our classical notions of cause and effect, hinting at a deeper connection that transcends our everyday experience. Wave tracing isn't just a theoretical concept, it has practical implications as well. Quantum computers, the cutting-edge technology on the horizon, rely on the principles of wave tracing to perform complex calculations. These computers harness the unique computational power of quantum bits or qubits, which can exist in a superposition of states. By manipulating and tracing the wave functions of these qubits, quantum computers have the potential to solve problems that are currently unsolvable by classical computers, revolutionizing fields such as cryptography, optimization, and material science. In conclusion, quantum wave tracing invites us to journey into the mysterious and mesmerizing world of quantum mechanics. It challenges our intuition, expands our understanding of reality, and holds the key to transformative technologies. As we continue to explore the depths of the quantum realm, the concept of wave tracing will undoubtedly remain a guiding light, illuminating the path to new discoveries and pushing the boundaries of human knowledge. So the next time you ponder the nature of particles and the intricate fabric of the universe, remember the captivating dance of quantum wave tracing, a delicate interplay of probabilities that shapes the very essence of reality itself.